Hello chemistry students, this is Mr. Ferguson and I'm introducing lesson 6.5 where we're going to take a look at Lewis dot diagrams and Lewis structures. So our goal for this lesson is to have you write Lewis dot diagrams for elements and then to combine those Lewis dot diagrams to make what's called a Lewis structure for simple molecules. This is a really useful tool for helping you to figure out how the atoms are going to bond together and the arrangement and the number of bonds that are going to form. And then it will also become a useful tool for predicting the shape or the geometry of the molecule, as you're going to see in a future lesson. So let's get started.
So what is a Lewis dot diagram? What they do is they only show the valence electrons of any given atom or molecule. So shown below is just a generic elemental symbol X. And what did you want to tell them about it then?
So what we do is we show little dots around the element symbol that represent only the valence electrons, only the electrons in the outermost energy level. And there's 4 sides. You can think of a top, bottom, and a left and a right. And we can put 2 electrons onto each side. So the first 2 would go together. That would theoretically represent our s orbital.
Probably should label it as such.
So
the
this
top
would be
2 would be the s orbital.
And it doesn't necessarily need to be the top. You can move them around.
Yeah, as long as they're paired up to begin with.
So this would be 1 and 2. All right, then the third one would go, say, over here. The fourth one might go down here. The fifth one over here. So that represents our 3 p orbitals. So this one's going to be px. Could be px.
One of the
3 py, and if those are px and y, this one's pz.
Or p negative 1, 0, and 1 if you want to use the quantum numbers we used.
Okay, then 3, 4, and 5. Then we go back. Now we following Hund's rule. We double up 6, 7, 8.
There we go.
So that if an element had all 8 valence electrons, like a noble gas, it's going to have 2 dots on all 4 sides. If it has 7, it's going to have
7.
Just 7 of them, and there's going to be 1 unpaired electron.
All right, let's show them some real-life problems from the periodic table then. So here we have some different group. We actually have, I believe, 8 different groups or columns to show you kind of an example of what we mean. And to get the total number of valence electrons, if you remember in class, I did mention it before, that column 1 here would have 1 valence electron. This would have 2 valence electrons, and you skip this entire section here, you have 3, 4, 5, 6, 7, 8 valence electrons. That's how you count to figure out how many valence electrons each element would have. So if you're looking at hydrogen, for example, you would find it in the first column, and therefore you would only have to put 1 dot. And if you notice, Mr. Ferguson's putting the dot off to the right. It doesn't really matter where you put the dots, as long as the 2 s dots are together to start. So the next one is beryllium. Again, we find that in the second column now. So you would need to put 2 dots next to each other because they're both s. Then boron, you go over, is in column 13, which would have 3 valence electrons. So 2 get paired together. There you go. Then carbon has 4. First 2 paired up, and they don't have to go on the right. I'm just showing them on the right. 1 over here and 1 somewhere else. 2 of the p orbitals are occupied by 1 electron. But it is important to make note, carbon is an exception to the rule of Lewis dots. Normally carbon has 1 dot on each side, but that's an exception that we're not going to deal with right now. Right. So we'll get into that maybe a little later. So nitrogen has 5. 1, 2, 3, 4, 5. Okay. Oxygen has, of course, 1 more than nitrogen because it's another column over. So 1, 2, 3, 4, 5, and then we can double up anywhere we want in one of these pieces. I'll put it there. Alrighty. Fluorine has 7, so we're getting closer to the octet. 1, 2,
3, 4, 5, 6, 7.
And then lastly is neon, which is in the 8th row. So that's going to be a noble gas for a reason, because they have a full outer valence. So please note how he does fill them in. It goes pair of 2, and then singles, and then pairing up again.
So as a good general rule then, how many covalent bonds something likes to form, as a general rule, would be seen by how many unpaired electrons it has.
Yeah, so like carbon actually has the 4 different ones, because
so we could actually say or C 1, 2, 3, 4.
That's what carbon's supposed to look like, and that's how you know carbon forms 4 bonds, why nitrogen forms 3, because it has the 3 openings, and oxygen likes to form 2, fluorine forms 1, and of course these guys form
none.
So
okay, hydrogen has just one unpaired electron, so it's going to form 1 bond. Beryllium's a little bit of an oddball, and actually is a metal, and it doesn't really do a whole lot of covalent bonding.
Boron's another special one where it can actually want to form 3, because it again, a lot of special rules, but just know the general rule at first. That's what we're looking for at this level.
So and hopefully if you didn't make any other connection here, like Mr. Hunter pointed out, the column number basically corresponds to the valence electrons. 1, 2, and then just looking at the tens place or the ones place, 3, 4, 5, 6, 7, and 8 valence electrons.
All right, let's look at some more practice.
Okay, so a little bit more background that you need to understand before we get into making molecules with Lewis diagrams that we call Lewis structures. We got to keep in mind that the octet rule, and we've covered this already, but the most stable electron configuration for an atom is when it's got a full S&P sublevel on its valence level,
which means 8,
which is 8 electrons.
Or if you are one of the 2 special elements that have a duet rule, it's hydrogen and helium. The first energy level is completely full, and that makes them stable. So that'd be hydrogen and helium only. They only want 2 electrons.
Right, so hydrogen wants to have those 2 to fill it up, and it's only going to ever form 1 bond. That's kind of a special case. It's sort of like the octet rule. We call it the duet rule. And basically, covalent bonding then, we've already covered this, but the atoms are going to share one of their unpaired electrons with a nearby atom that also has an unpaired electrons, and then they can satisfy that octet rule in that way. And again, this usually involves the sharing of these half-filled or the lone electrons that don't already have a pair. A filled sublevel or filled orbital is stable as it is, but an unfilled orbital is unstable.
And shown down here, we have drawn a single bond where you see they're sharing 2, a double bond where they're sharing a set of 4, and a triple bond is where they're sharing 6. So that's just to illustrate what a Lewis dot bond would be drawn like.
And how does, let's look at our triple bond. How's the octet rule satisfied? Well, each atom has 2 electrons of its own, and then the 6 shared ones count as electrons of both atoms. So 6 plus 2, this one on the left has 8, and the one on the right also gets 8. So sometimes they'll do a triple bond. But you can see the same idea with our double and single bond. The atoms end up with 8 electrons in sharing to satisfy the octet rule and be stable.
Indeed. So the first thing you should do is probably write down what's written at the top there or typed at the top. It's a good way for you to continue to make Lewis structures on your own. But first of all, we always have to find the total number of valence electrons for any atom. So we can start down here with carbon tetrachloride. We know carbon brings 4 electrons, and each chlorine brings 7. So that's 28 plus 7, which equals, of course, 32.
So we have 32 electrons that we need to put into our Lewis dot structure. And we need to decide on the structure. Many times there's a central atom, and then everything's bonded to it in one of these simple atoms. So we need to decide on that. As a rule, the first thing in the formula is the central atom, usually.
It's always usually carbon. So
carbon. If you have carbon, that's the central atom.
So the first thing you would draw for this would be carbon. And then we have 4 chlorines, so just draw 4 chlorines, equally distanced apart.
And after a while, you get a feel for this. You don't have to kind of figure it out. Like, you're going to know that's the way it's built.
And then I start filling in electrons
So the first thing we
around
do,
the central atom.
we know that there's at least a covalent single bond between carbon and each of these chlorines.
Yeah.
So we're going to put our pair of electrons representing the covalent bond for each of these.
That gives us 8, so we need 24 more.
Okay, so we've placed a pair of electrons between the bonded atoms. We're going to move on to the next step. We're going to complete the octets of the outer atoms if needed. Like if it was hydrogen, we wouldn't need to, but for chlorine, it needs a stable octet. So we're going to put 8, or finish filling in 8 around each one of these. So I need to add 3 more pairs to each chlorine.
And you could be counting as you go, but we're experienced enough to know that they're all going to have an octet when we're done.
So we want to check, does our central atom have an octet?
Yep.
Mr. Hunter already said that it does.
Do our outer ones all have octets?
They all have octets. And now the final check is, did we use all 32 electrons?
The answer is we did.
We did. If you count them, there's 32. So that is a correct Lewis structure for carbon tetrachloride.
All right, let's do another one here. I guess we can do NH3.
Okay, so again, nitrogen, there's only one of them. It's the first thing. I think that's probably the central atom.
And it brings 5. And then there's 3 hydrogens.
So we're going to put the 3 hydrogens around there. Nitrogen has 5, like Mr. Hunter said. Each hydrogen has 1, so that's 5 plus 3. So we have a total of 8 electrons or 8 dots that we need to put in. Let's bond each hydrogen to the central atom.
There, we used 6.
We don't need to complete an octet on the outer ones, but nitrogen only has 6. It doesn't have an octet.
So it wants another set of 2 to make the final 8.
And it has an empty orbital at the bottom. So we're going to put 2 there. This is called an unbonded pair or a lone pair of electrons, which we need to show. It's going to be important to the geometry and to the chemical properties of the molecule. And we've got an octet on our central atom.
Probably label that as a lone pair. I don't know if we've talked about them before.
That's a good idea. So we'll make that. This is a lone pair, also known as an unbonded. Unbonded pair. Okay, so that's 2 out of 4.
So next is oxygen, O2. Each oxygen brings 6, so we want a total of 12 when
So
we're
we
done.
need 12 dots, and now this is a diatomic, so there's no central atom. It's just O
Next to
O. So we start by bonding the 2 oxygens together.
Mm-hmm.
We complete their
So that's
octets.
2, and then you can 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.
Now the problem is
We ran out of electrons.
We ran
before
out of
our
electrons.
Before other oxygen got a
okay, so
full
this is
octet.
where we want to, since we don't have an octet, we want to look for a way to form a double or triple bond. If you run out of electrons, that would be an indication we need to take a pair of electrons from the one that has more and move them in here.
So in between. So then they should have.
Erase. That doesn't want to erase.
Because you drew it before we started.
So let me.
Redraw it.
I'm going to X those out. They're not there anymore. They are now down here. So that is how we draw. Now another alternative way we can do that. Every time we have a pair of electrons shared, we can show a bond line instead of the pair of electrons. So you could also write O2 in this way. Since they're sharing 2 pairs, we'll show 2 lines. And then we actually have 2 lone pairs or unbonded pairs on each oxygen. So every one of those lines counts as 2 electrons. So if you count, there's 12.
Yeah.
2, 4, 6, 8, 10, 12.
Okay.
So oxygen double bonds to itself.
And then the last one here, CO2, we have a carbon, which would be the central. And then we have 2 O's, so that would be 4 plus 12.
So that's 16 electrons.
Yep, so let's first set up our carbon.
So we're going to give carbon a
2,
covalent bond
3,
to each
4.
oxygen, and then we're going to complete the octet of each oxygen. That's 5, 6, 7, 8, 9, 10, 11, 12,
4 more.
13, 14, 15, 16.
There we go.
Now, where the issue is here, we've used all the electrons. Oxygen each has an octet. Look at carbon.
Yeah, the carbon's
Does
missing.
not have an octet.
Is missing 2 sets of electrons. So each oxygen is going to donate a set to be shared, and then you'll have 2 double bonds in between.
So we're going to rewrite this here, here, here. Whoop, that's 2 pairs. That's 1 pair. There's the other pair.
There we go. So that gives us a total of 8 per atom, and that gives us a total of
16 electrons. So we could also rewrite this as we showed up above, showing the double bond to both oxygens, and then don't forget to show the lone pairs on each oxygen. And we went slow through this because this is oftentimes a difficult skill for people to catch on to. We'll be doing lots more examples in practice in class.
We have one more type of this. It's called for ions. So let's go take a look at those.
So the final thing we want to look at in this lesson is doing the Lewis structure for a polyatomic ion. And it's really no different than doing the Lewis structure for a neutral molecule like we just did, with the exception that we have to remember that these are ions, so they have some extra electrons in their structure in addition to what the atoms brought with them. At least if they're anions, they're going to have extra ones. If it is a cation like ammonium, of course, we would have to adjust by removing an extra electron. So let's take a look at the first one is a hydroxide ion, OH minus. And again, the first thing we want to do is write the 2 atoms next to one another. So we're going to write oxygen and hydrogen. The next thing we want to do is add up the total number of electrons that we need to include in the structure. So again, oxygen has 6 valence electrons. A hydrogen has 1 valence electron. And then we have to remember that the -1 charge is also going to be an additional electron. So this structure is going to need to have 8 electrons in it. So the first thing we do, we know there's going to be at least a pair of them bonding the oxygen and hydrogen, so we draw that shared pair of electrons between oxygen and hydrogen. And then we're going to, since there's just the 2 atoms, we would need to complete the octet of both of them. So I'm going to complete the octet on hydrogen. There's 2, there's another 2, there's another 2. Did I just say hydrogen? We're going to complete the octet on oxygen. Now we're not going to complete the octet on hydrogen because, again, hydrogen follows that duet rule. Once it gets 2, which it has by sharing this pair right here with oxygen, that's a stable arrangement for hydrogen. So this would be the correct Lewis structure for hydroxide ion. Now generally we also would bracket it and put a -1 on the outside to show that there's actually an extra electron in this whole particle is going to be carrying an overall -1 charge, because there's actually only 7 electrons in an oxygen atom and a hydrogen atom, so there's an extra one in the structure. There's 8 in the structure. Now we have a carbonate ion for our second example. So that's 1 carbon and 3 oxygens with a -2 charge. So again, carbon, as soon as we see that, we know that carbon's going to be our central atom, and we're going to arrange 3 oxygen atoms around that carbon. So it's definitely going to be arranged in this manner. The next thing we need to do is figure out the number of valence electrons that we are working with in this structure. So carbon, we should know by now, has a total of 4. There's 3 oxygen atoms. Each one brings 6. So that's 6 times 3. So that would be 18 electrons on the 3 oxygen atoms. And then I'm going to add 2 more because we have that -2 charge overall. So that tells us there's 2 extra electrons above and beyond what the carbon and the oxygens had. So that adds up to a grand total of 24 electrons that we're going to place in our structure. So again, we will begin by adding a pair between carbon and each of the oxygen atoms. That's the first step. The next step is going to be to complete the octet on the outer atoms. So again, I can just see by looking at it, oxygen's got its octet satisfied. We'll do the same thing for the second oxygen. Okay, so we have, let's check and see how many we've used at this point. We have 8 around this one. 8 around this one, that's 16, plus those 2. So we've used 18 out of our 24, so we only have 6 electrons left. So, 1, 2, 3, 4. So I have 2 more. Now I can see right now I have an issue. Carbon needs 2 more right here in order to satisfy its octet. This carbon atom is only going to have 6. If I put the remaining 2 electrons in that empty orbital around oxygen, carbon's left without an octet. That's not going to be a stable arrangement. So that means we have to look for a double bond opportunity. So we're going to double bond one of these oxygens to the central carbon atom. Okay, and again, we know it's an ion, so we're going to bracket it and give it a -2 charge. So that's a carbonate ion. Now, for those of you that are wondering, well, why did I choose this one? I just kind of randomly picked that oxygen atom. It actually could be any one of the 3 has the double bond, and in fact we could draw that structure with the double bond here and a single bond here. We could draw that structure with the double bond here and the single bond in these 2 positions. All 3 of those structures are what we would call valid, and that gives us what we call a resonance structure, which we'll discuss later. And in fact, when they actually do laboratory investigations of the carbonate ion, what we find is that all 3 of the bonds are somewhere between the length of a covalent single bond and a covalent double bond. It's kind of like they're all like a 1.5 bond. That shared pair of electrons seems to hop around between the 2, and so we get 3 bonds that are kind of all intermediate in length. But that's a subject for a future lesson. So anyway, that's our polyatomic ions, much like doing a regular Lewis structure. Lots more practice tomorrow in class. Until then, I'll see you.